Hey everybody, this is the final chapter for Chem 104. We're going to go over some select topics from Chapter 11 on acids and bases. It will be related to some of the things that we talked about in Chapter 9. We're going to start with Section 11.4, which is on the dissociation of weak acids and bases. This is very similar to what we were talking about with weak electrolytes. That was in Chapter 9. So you'll recognize some similarities. We're going to learn how to write dissociation expressions. We're also going to learn about acid dissociation constants and things of that nature. So before we talk about weak acids, let me remind you that a strong acid, which is also a strong electrolyte, again, Chapter 9, that's going to be something that completely dissociates in water. So there's no equilibrium there, you just have ions. Weak acids, however, they partially dissociate, which means that you've got some ions, but those ions reach an equilibrium with undissociated weak acid or weak base. One example of a weak acid is formic acid. It dissociates in water to form hydronium, which is H3O+. You may have seen it written as H+ in high school chemistry. It's the same thing, it's just it's a more proper term. And then we also have the formate ion, which is a negative ion. If you take some formic acid and add water, we're looking at this equation down here, then you end up making some hydronium ions and some formate ions. These forward and backward arrows, this means equilibrium. And just as a reminder from when we were looking at chemical equations, the left-hand side, these are the reactants. The right-hand side, these are the products. If those chemical equation, kind of that know-how is a little bit rusty, go back and look at that chapter again. I believe it was chapter 7 where we looked at chemical equations. You'll need to be able to write that dissociation equation so that you can write a dissociation expression. With this dissociation expression, what we're talking about is molar concentrations of the products divided by the molar concentration of the reactants. So if we're looking at, again, this formic acid example where we're mixing it with water, the reactants that we're interested in, we're only interested in the formic acid. We're not interested in the water because it's a pure liquid. So when we're writing our dissociation expression, we're going to ignore it. That's why I put an X over it. We are, however, interested in both the hydronium ion and the formate ion. The dissociation expression, that gives you the Ka, which is the acid dissociation constant. And that is equal to the molar concentration of the products, which we represent in brackets, H3O+, and CHO2-. Those are our products. Over, in this case, we only have one reactant, and that's the formic acid itself. So that's always going to be the form, the generic form, products over reactants. And in those little brackets, that means that we want the molar concentration. But why do we care about dissociation expressions and Ka values? Well, the acid dissociation constant, the Ka, can tell us about the acid itself. If it's a small value, then that means that the equilibrium lies to the left, which means that it favors the reactants. I'm going to write up here the what we were looking at before with this equation for formic acid, so we can have some kind of an example. So, when equilibrium lies to the left, that means we're talking about the reactants. If you have a lot of the reactants, then that means that you have a lot of undissociated weak acid. So that Ka value is going to be small. If it's large, then the equilibrium lies to the right, which is the product side. So you're going to have large amounts of ions, specifically the hydronium and whatever other conjugate base that you form. We'll talk about that in a second. So weak acids, small Ka values. Strong acids, very large. In the case of formic acid, it has a Ka value of 1.8 times 10 to the minus 4. Notice how there's no units here. And again, that expression, we have the hydronium ion, the formate ion on the top, and the undissociated formic acid on the bottom. Ten to the minus 4 is small. So that means formic acid is a weak acid. The same thing is true for the base dissociation constant, which is called the Kb. If you have a small Kb, then the equilibrium lies to the left, which means that you're going to have undissociated weak base. That's what your reactant is. If it's large, then your equilibrium is going to lie to the right in favor of the products, which the products are the ions. In this case, we're talking about hydroxide, which is OH minus. The stronger the base, the larger the Kb value. So here we have an expression for a base. It's an equilibrium, as shown by these two arrows. Anytime an acid or a base is shown to be in equilibrium with its ions, that's another indicator that you're looking at something that's weak and something that partially dissociates. Notice how for the Kb expression, the concentration of water is omitted. So we've only got the products up here, and then we have the one reactant. We do not include water here. And 4.4 times 10 to the minus 4th, that is small. So that means you have a weak base. So same logic for acids and bases. This table just gives you some examples of acids and their Ka and Kb values for bases. It gives you an idea of kind of what the range is of some of these different acids that you may encounter in class, or in the lab. Particularly if you're doing any kind of biochemistry work, you'll definitely run into phosphoric acid. So that's just something to keep in mind. This table, 11.5, summarizes the characteristics that we've been talking about in terms of where the equilibrium lies for a strong acid versus a weak acid, dissociation, those kinds of things. So it's for strong acids and bases, weak acids and weak bases. So this table can help you when you're doing your homework, and it can help you study. Now let's do a learning check. I know we did this one in class, but I'll be able to go through it a little bit more slowly, and you can rewatch it as many times as you want. Yay, right? So we've got to write the acid dissociation expression for nitrous acid. Before we can write the expression, it's a good idea to write out the equation to show how it will dissociate in water. So if we have nitrous acid that is aqueous, and we add some liquid water, now notice I do half arrows, it's the same thing. Still means equilibrium. If we dissociate, we're going to form hydronium, which is that H3+, and we're going to form NO2-. Now that we know what our reactants and our products are, we can write the expression. We don't include water. We only want the ions, or the things that are aqueous. So we're going to include only the things that I'm circling in the expression. The products go on top. And then the reactant goes on the bottom. And that is the dissociation expression. Now to take it a step further, let's say that we need to estimate whether or not this Ka is going to be big or small. Since it's an equilibrium and there's only partial dissociation, we can guess that the Ka will be small for a weak acid. So make sure all of those things connect in your mind. Small Ka, weak acid, partially dissociates. Now we're going to take that knowledge of writing dissociation expressions and apply it to water. Water is very special for the chemist and the biochemist in particular, because water is such a great solvent. Biological systems all need that water. And water can do a lot of wonderful things. And one of the crazy wonderful things that water can do is it can act as both an acid and a base. And we'll talk about that quality of water and what that means. So the ability to act as an acid or a base is called amphoteric. If you have water, you can have two molecules of water. One acts as an acid and one acts as a base. The one that acts as an acid will transfer a hydrogen ion to the other molecule. And water is in equilibrium, where you have some of these ions in solution. So let's say we have our water molecules. This is water molecule 1. This is water molecule 2. Water molecule 1 is going to donate this hydrogen. Which means that it is going to be an acid. And it is going to end up onto water molecule number 2. When that happens, you form hydronium, H3O+. Now this is an acid. As you can see, it's labeled an acid down here. Acid means that it can donate a hydrogen. And what we've created is a base, something that can accept a hydrogen. We've made conjugate acid-base pairs. When water molecule number 1 donates its hydrogen, it becomes a base on the product side. So it goes from being an acid, it gives up its hydrogen, and now it's a base. It's just the OH minus. On the flip side, we've got water molecule 2. It started off as a base because it accepted a hydrogen from water molecule 1. Once it accepts that hydrogen, it's now hydronium, that H3O plus ion. It's got an extra hydrogen to donate to the cause, so it is now an acid. The one that's formed on the product side is called the conjugate acid and the conjugate base. Let me get my colors right here. So that's conjugate acid-base pairs, specifically with water. Again, we have this relationship written out here where we've got 2 water molecules. One acts as a base, one acts as an acid. The base will accept a hydrogen to become a conjugate acid, the hydronium ion. The water molecule that acts as an acid will give up one of its hydrogens to become a conjugate base. In pure water, at 25 degrees Celsius, the concentrations of each the hydronium ion, which is the H3O plus, and the OH minus, that's hydroxide, both of those concentrations are 1.0 times 10 to the minus 7th molar. If we were to write a dissociation constant expression for water, well, we only include the things that are not pure liquid. So we wouldn't include any water on the reactant side. So that KW, which is the dissociation constant for water specifically, is only going to be equal to the concentrations, you multiply the concentrations of both of these ions. There's nothing in the denominator because the reactants are both pure liquids. So this is a special case. And you'll want to know that this KW is 1 times 10 to the minus 14th. That's definitely something you'll want to know. Again, this is specifically for water at 25 degrees Celsius. For the KW and for the KAs that we were talking about in KBs, you don't have concentration units in the constant. And when we look at the concentration of the hydronium and the hydroxide, we can tell whether or not a solution is neutral, acidic, or basic. When the concentrations of hydronium and hydroxide are equal, the solution is neutral. If you have more hydronium than you do hydroxide, then the solution is acidic. If you have less hydronium than you do hydroxide, in other words, there's more hydroxide, then your solution is basic. And we're going to be talking about a few ways of how to tell whether a solution is acidic, basic, or neutral. This is just one way to describe it. They all mean the same thing, but it's about the terminology. I would definitely recommend that you make a table at the end that shows all the different ways that you can describe an acidic solution, a basic solution, and a neutral solution. Why do we care about the KW? If we have something in solution and we add an acid or a base, we can actually calculate the concentration of hydronium and hydroxide. And we can use the KW to do that. So this was the dissociation expression for water. You can rearrange that to solve for hydroxide and hydronium. And we'll do an example of that shortly. But remember, these are equations. We can manipulate them just like we do any other equation. This is just, we're going to go through a few slides of kind of visualizing the different levels of hydronium and hydroxide before we do a sample problem where we manipulate the KW and the hydronium and the hydroxide. So again, pure water is neutral. Any neutral solution, you're going to have equal levels of hydronium and hydroxide. In an acidic solution, you've got an increase in the hydronium. So see how the red bar, that's the hydronium, that's now higher than 10 to the minus 7. With a basic solution, it's the opposite. You increase the hydroxide, so it will exceed that 1 times 10 to the minus 7 molar, and the hydronium will drop down. That's a basic solution. This slide is just a comparison of all of them. So if you have equal, and your equilibrium goes this way, your acidic, the other way, basic. So if you're a visual creature, this is a great way to kind of visualize the levels of hydronium and hydroxide and what's happening to them as you become acidic and basic. This table has some examples of concentrations of hydronium and hydroxide in neutral, acidic, and basic solutions. So you should be able to look at the concentrations and know whether or not something is acidic or basic. Now let's do some math. Let's say that you have a solution and you know the hydroxide concentration. What is the hydronium concentration? Like I said, we have to use that the KW for water. So that is KW, which is equal to 1 times 10 to the minus 14, is equal to you multiply those two together, right? Now we need to rearrange and solve for hydronium. To do that, we're going to just divide by the hydroxide concentration on both sides. Now we know what this concentration is. We can fill this in from the problem. you need to do that division and make sure that you remember how to put in numbers and scientific notation in your calculator. So even if you understand the math, make sure that you can use your calculator properly. There's going to be a couple of more places in this lecture where you should definitely check to make sure you can get the right answer. Not because you have to check the math because the math is difficult, but simply because you need to know how to use your calculator and you don't want to be at the exam saying, oh, wait, so what? That's a bad place to be. So make sure that you practice, and in class, we're going to do practice problems as well. When you put this into your calculator, you should get 2 times 10 to the negative 7. And because we're talking about a concentration, it should be molar. If you don't get that, play around with your calculator until you do, and then figure out how you got there. And when in doubt, always ask Google. Google knows how to use your calculator, okay? All right. So we talked about the concentration of hydronium and hydroxide. That will move us towards talking about the pH scale, which is another way to describe the concentration of hydronium. The pH of a solution, we're talking about acidity. The values usually range from 0 to 14. When something is acidic, your pH is less than 7. When you're neutral, you're right at 7. So that's that pure water. And when you're basic, you're greater than 7. Down here is a good kind of representation of acidic, neutral, and basic, what their pHs are, and it relates that to the hydronium concentration. So this column is really key. Make sure that you understand this. For an acidic solution, you're going to have a hydronium concentration that's greater than 1.0 times 10 to the minus 7 molar. pH 7, that's neutral, it's going to be equal to 1 times 10 to the minus 7. And for a basic solution, that hydronium concentration will be less than 1 times 10 to the minus 7 molar. Again, make sure you understand that. The pH of a solution can be measured a few different ways. You can use what's shown in A, which is a pH meter. That's the most accurate way to do it. You'll get an exact number, more or less, of what your pH is, and you can adjust your pH of a solution right there on the spot. Very easy. Another way is to use pH paper. So that's just paper. You may also see it called litmus paper. It's the same thing. You take the strip, you dip it into your solution, and then it changes color, and that color corresponds to one of the colors that's on the package. So you can see going all the way from 0 up to, there's up to 11 on the front. Some of them will go all the way up to 14, and you have to turn it over to see the rest of the colors. But just the color that the paper changes to indicates what pH it is. Now, you're not going to know that it's 8.2, but you can say, it's somewhere around pH 8. So sometimes that's all you need. In C, what we're looking at is indicators. So indicators are chemicals that will, there's chemistry that happens when they reach a certain pH, and that causes a color change. That color change indicates you've reached at least this pH. So it's not exactly fancy, but it is pretty. That's one thing it has going for it. So if you need to be very precise, you need to use the pH meter. If you just need to know the ballpark, B or C would be the answer, the pH paper or the indicator. And this just talks about some of the common things that you encounter, like different types of juice, coffee, bleach, other cleaning solutions, and things of that nature, to give you an idea of where these things fall on the pH scale. So you may, if you really enjoy carbonated beverages, you should know that they are quite acidic at around pH 3. So please be careful, take care of your teeth. Coffee as well is on the acidic side with a pH of about 5. Your blood plasma is slightly on the basic side. And then things like ammonia and bleach, cleaning agents, they are quite basic. So those are caustic and they can do damage to your skin, so be careful. We can calculate the pH of a solution if we know the concentration of hydronium in that solution. The equation that you'll use is here. The pH is equal to the negative log of the concentration of hydronium. This log function is something you will need to find on your calculator. If you have a TI-89, then you have to look in the catalog. I know that because that's what I have. If you have an 83, you may have a log button, but you may also need to go to the catalog. But it may look something like this, a log button like that, or it could say log 10, but you're looking for log base 10, not base 2, base 10. Make sure that you know how to use the log function on your calculator because you will need it to do pH. We also have to talk about significant figures. So significant figures with pH is a little bit funky, a little bit different. To determine the number of significant figures in a pH value, you have to put a certain number of decimal places. Okay, so if we have a hydronium concentration of 1.0 times 10 to the minus 2, which is quite acidic, we've got 2 significant figures in the 1.0. To represent that, we're going to put 2 decimal places in the pH. So this number here is a freebie. You have to put that number. But the numbers that come after the decimal point, that's how you represent how many significant figures you have. So if you had 1.00 times 10 to the minus 2, here we've got 3 significant figures. So the pH would have to have 3 zeros afterwards, after that decimal point. So that's how you do significant figures for pH. Now the pH scale is a log scale. So if you go from a pH of 2 to 3, it's only a change of 1, but what that really corresponds to is a 10-fold change. So if you go from a pH 2 to a pH 3, then we're talking about an entire exponent difference here, okay? So that's a pretty big jump. The pH decreases as the concentration of hydronium increases. And I'm a very visual person, so I'm rewriting it for those of you who are like me, who like to see the up and down arrows. So decrease your pH means that you're increasing that hydronium concentration. Now let's try a calculation. Aspirin, which we're all familiar with, is acetylsalicylic acid. It was the first non-steroidal anti-inflammatory drug, which you might see as NSAID. That's what that means, non-steroidal anti-inflammatory drug. And it's used to alleviate pain and fever. If a solution of aspirin has a hydronium concentration of 1.7 times 10 to the minus 3 molar, what is the pH of the solution? Well, just by looking at the concentration of hydronium, it is definitely greater than 1 times 10 to the minus 7. So we know that this solution should be acidic, which means that it should have a pH less than 7. Those are two things that we know just by looking at the concentration. I can't tell you off the top of my head what exactly the pH will be, but I know that it should be acidic, which means it's less than 7. Don't forget to use your logic like that, because if your calculator tells you something weird, you need to be able to diagnose that and try again with the math. So our equation for pH is negative log, don't forget that negative, of the hydronium concentration. This is where you will need that log function. When you put that into your calculator, again, please don't forget the negative. If you don't have the negative, then you're going to end up getting a negative answer. Your calculator will tell you 2.769 or something like that. For the pH, we have to put the number of decimal places that's equal to the number of significant figures in our hydronium concentration. In our hydronium concentration, we have 2 significant figures. So that means that for our pH, we need to have 2 decimal places. So your pH is equal to 2.77. Cannot stress enough, know how to use your calculator. If you do not know how to use your calculator, ask Google. Google knows. Google knows most things. So look up your calculator. You can find a video on YouTube. You can find whatever kind of how-to, instruction manual for your calculator. Make sure you know how to do it. So we covered how to calculate pH from hydronium concentration. You can also do the reverse. You can calculate the hydronium concentration from the pH. This is the equation we're going to be using. So let's say that I had a pH equal to 1.0, oops, not 1.0 like that. I'm thinking about the hydronium concentration. Let's say that I had a pH of 5. That would mean that with this equation, that would equal my hydronium concentration. But if you don't have a whole number, you're going to have to do some math. So if my pH was instead equal to 5.3, then I have to use that 10x key on the calculator, which is usually a second function key. You may also have something like 10 with a caret, 10 with a y, or that 10 with an x. So there's lots of different ways that your calculator may have that kind of function key, but you'll need to know how to do the reverse of the log. So let's practice that. Determine the hydronium concentration for a solution that has a pH of 3.42. Again, don't forget that negative here, because it is a big difference. 10 to the negative something versus 10 to the positive something. When we just put in what we have, our pH is 3.42. you'll need to find that little button that we talked about. Make sure you can put that into your calculator. Let's figure out how many significant figures we should have for this. Remember, our pH, the number of decimal places, tells us how many significant figures for our hydronium concentration. We've got 2 decimal places here, so that means 2 significant figures in our hydronium concentration. So you should get 3.8 times 10 to the minus 4 molar for the hydronium concentration. And let's make sure that that makes sense. So, pH of 3.42 means that it's acidic, right? Less than 7, acidic. That means that our hydronium concentration should be greater than 1.0 times 10 to the minus 7 molar. And it is. So that checks out. Doesn't tell you it's exactly the right number, but at least you can double check and make sure that you didn't goof with your calculator. Always make sure to do those mental checks. They will save you points and they can boost your score. The final section for Chapter 11 and the final section for Chem 104, I can't hear you cheering, that's okay, so you can let it out. We're going to talk about buffers. Now, buffers are near and dear to my heart as a biochemist. When you're dealing with biological systems, or you're trying to replicate a biological system, or take a piece out of a system and use it on the benchtop, buffers are clutch, okay? So forgive me if I'm a little bit excited, because this is something that is near and dear to my heart. But with that said, let's keep going. What is a buffer? Well, a buffer is simply a solution that maintains the pH by neutralizing small amounts of acid or base that are added to it. If you were to just add an acid or base to water, the pH would just change really drastically. And that's what's shown in this example, where you've got water. If you add some acid, you can go from pure water, which is pH of 7, down to 4 just by adding a few drops. Likewise, if you have pure water and you added just a few drops of base, boom, you could raise your pH up to 10, 10.5. So there's no buffering capacity in water really at all. However, if you have a buffer solution and you add a few drops of an acid or a few drops of base, you don't see the same wild fluctuation in your pH. That's really, really handy when you're dealing with biological molecules like proteins and things that are sensitive to acids and bases. You need to have some kind of a buffer solution that keeps them at a pH that makes them happy. Yes, proteins can be happy. Don't question me. That's just what it is. Okay, how do buffers work? They work because they resist changes in pH, right? In the body, they work because they absorb all of that, the hydronium and the hydroxides and things from the foods that we eat and the cellular processes that go on in our body, right? So remember, there's a lot of chemistry that happens in our bodies. And as a result of that chemistry, sometimes you make something that's acidic or basic. So you need to be able to adjust and make sure that your tissue fluids and body fluids and all those things are at a happy pH for all the chemistry that's going on. Buffers are very important for the proper functioning of cells and blood, okay? In blood, your pH is around 7.4. And if it varies outside of that too much, you can actually become quite sick. We'll talk about that. We'll talk about the buffering in the blood and what the results are if your pH is a little too high or too low. So what makes up a buffer solution? It's a combination of an acid-base conjugate pair, and we talked about that when we talked about the dissociation of water. But that same concept applies to any acid or base that you're putting into water. If we have acetic acid, which is this HC2H3O2, and we have the acetate ion, that's an example of an acid-base conjugate pair. If you lose this hydrogen, right, you donate this one, then you become the ion. A buffer solution has both of these, a large concentration of both the acetic acid, or your weak acid, and a salt of its conjugate base. And that just means something that's going to dissolve and make the conjugate base. So with our acetic acid example, if we pair that with sodium acetate, which again is something that will dissolve in water and give you the acetate ion, as you can see in this equation here, we're providing a really large amount of both the acid and the conjugate base. That's important because that means that we can absorb some of the extra hydronium or the extra hydroxide from a little extra acid or base. Let's say that we add a little bit of base to the solution. So we're starting off with equal amounts of weak acid and conjugate base. We just made this buffer. And then we drop in a few drops of base. That base is going to interact with the acid because a base accepts hydrogens and the acid donates one. So that little bit of base that we added will accept the hydrogen from that big amount of acetic acid that we have in solution. And we're going to make that acetate ion, which is our conjugate base. And we're going to make some water. When we do that, we change the balance a little bit of the buffer to where we now have more conjugate base than we do the acid. It's still a buffer, it's okay, but that's what happens when you take a buffer and you add a little bit of base. When you have a buffer and you add a little bit of acid, then we have something different happening. Our acid is the H3O plus, and that is going to interact with that acetate ion. The acetate ion is going to take up that hydrogen from the acid to make more of your acetic acid. So if we had that same balance of the weak acid and the conjugate base, equal amounts, we added in an acid, we're now going to have more of the acetic acid, which is our weak acid. Then the conjugate base. So with these equilibrium shifts, it takes a little bit of practice to kind of understand it. We'll try to walk through an example or two in class to make sure that you understand how the equilibrium is affected when you add a little bit of acid or a little bit of base to a buffer. So this slide just kind of summarizes what we talked about over the course of 2 slides. What happens if you add acid, and what happens if you add base. So it puts it all together for you on the same slide. And the pH is more or less kept the same in both scenarios because we're not varying too wildly from our buffer solution, the original one that we started with. We can do some calculations when it comes to a buffer. Remember the Ka expressions that we were talking about in the beginning, where you have the products over the reactants? That tells you the Ka, which is the acid dissociation constant. We can get the ratio of acetic acid to the acetate by solving for hydronium. So if we rearrange this equation, the dissociation expression, we can figure out how to calculate a ratio for our buffer. So this is, remember, the molar concentrations. This will help us if we're trying to make a buffer. So if we know what the Ka is, and we're given the concentrations of both the acid and the conjugate base, then we're able to calculate the pH. But it's just it's a 2-step process. So I'll walk through it. First, let's write the dissociation expression. The Ka, we're looking at the products, only the things that are aqueous. Over the reactants, again, only the things that are aqueous. So we see the water, but we don't see the water. We don't care about it for our equation. Now, if we solve for the concentration of hydronium, I'm breaking it down for you in steps. So the first thing that we did was just multiply by that acetic acid concentration on both sides. Now we're going to divide by the acetate concentration. And then I'm just going to rewrite it. So that's how you rearrange and solve. Just wanted to show how to do that. Now that we have our equation, we can put some numbers in. The Ka was given to us in the problem along with the concentrations for the acetic acid, which is 1 molar, and the acetate ion, which is also 1 molar. So that means our hydronium concentration is going to be 1.8 times 10 to the minus 5 molar. We're not done yet. What is the question asking? It's asking for the pH. So we have to say, now that we know our hydronium concentration, let's plug that in to the equation we know for pH. I can't stress this enough. 1, make sure that you have the negative sign in front of the log. 2, make sure that you know how to use the log function on your calculator. I cannot help you. I cannot see your calculator. I do not know every calculator that has ever been invented, but Google certainly knows more than I do. So use your resources. Make sure that you can use that log button. When you put all that into your calculator is going to spit out a bunch of numbers. We need to figure out how many significant figures we should use. So our concentrations have 2 significant figures. The Ka also has 2 significant figures. So that means with our concentration of hydronium, it's still 2 significant figures. Now that we've got 2 sig figs, that means that we need to have 2 decimal places. So this 4 is the last retained digit. So our pH is 4.74. Now with this question, if you understood how to do this and get as far as calculating the hydronium concentration, but you stopped there, if that was an answer on the exam, you would have been tricked. So always go over the question and make sure you're answering what the actual question is before you lock in that answer. Now we're going to talk about calculating the pH of a buffer. At any given temperature, that Ka value, the acid dissociation expression, the constant, it's constant. That's why it's called a constant. The ratio of the acid to the conjugate base determines the hydronium concentration. When you add a little bit of acid or base, it doesn't really change the ratio that much. If you add a large amount of acid or base, then you can exceed what's called the buffering capacity of the system. Each system can only handle a certain amount of acid or base before it can no longer buffer, and you're going to see that drastic change in pH when you add more acid or base. So buffers can be prepared from conjugate acid-base pairs, like we were saying. And there's lots of options out there. You choose the conjugate acid-base pair based on what the pH is you're trying to maintain. So each acid-base pair can kind of maintain a certain pH a little bit more easily, just based on, the chemistry of what those molecules are. So when you're making a buffer for, an experiment or something like that, you want to choose a combination that's going to be close to what you need so that you don't have to do a lot of fancy footwork to, get your buffer to the correct pH. It's a real pain. So let's look at phosphate buffer. Like I said, we use phosphate buffers a lot for a biological specimen. It's a really great buffering system. There's our acid and conjugate base. And our Ka is 6.2 times 10 to the minus 8, which is again pretty small. If you were to write the equation for dissociation, and then again write the expression, you'd be interested in these species. If you were to write that dissociation expression, I'll write it out, what it would have been before rearranging it. You'd have your hydronium and the HPO4 2 minus on top, and the H2PO4 minus on the bottom. Then you can rearrange and solve for the hydronium concentration. And that's what we did in that last problem. So that's where we are here. This ratio is what determines the hydronium concentration. So if we put in different values for the acid and the conjugate base, we have different ratios, and that has an effect on the pH. So if you have 10 times more acid than you do conjugate base, then you're going to have a pH of about 6. If they're equal, the acid and the conjugate base, you'll have a pH of about 7. So that's a major change. It's a 10-fold difference. We went from 10 times the amount of acid to now they're equal. And that corresponded to a change of 1 pH unit. If we were to then have the ratio be 1 to 10, where there's 10 times more of the conjugate base, then we again increase our pH by 1 unit to 8. So changing this ratio has a drastic effect on the amount of hydronium, which means it has a drastic effect on the pH. So why do we care about this? I mean, it seems like kind of a lot of mumbo jumbo, and it's okay, great, the pH changes, but why? Why do we care? Well, if you like being healthy, then you should know part of why you're healthy is because your blood plasma is of a normal pH. The normal pH is around 7.4. A little bit of wiggle room. If your pH becomes too acidic, so below 6.8, or it becomes too basic, above 8, your cells cannot function. They will die. So it is really critical that your body maintains the proper blood plasma pH. For us, carbon dioxide is integral to this. It is made all the time in your body. It's one of the end products of cellular metabolism. It's carried to your lungs to breathe out. It's called eliminating. And the rest of it dissolves in your body fluids, so in your plasma, in your saliva, and you form what's called carbonic acid. It's a weak acid. So when it dissociates, you get bicarbonate and you get hydronium. And I'll write that out for you. So that is the equation. In addition to cellular processes and metabolism, your kidneys also supply more of that bicarbonate anion. So just like we were talking about with the buffers that we make on the benchtop, where you've got a large amount of weak acid and a large amount of conjugate base, we have, relatively speaking, a large amount of the carbonic acid that's made from carbon dioxide dissolving in our body fluids. And we also have a large amount of the bicarbonate anion, because in addition to just the normal equilibrium of carbonic acid in our fluids, the kidneys are also supplying some. This makes up the buffering system in our blood. When you have excess hydronium entering your body fluids, it's going to interact with the bicarbonate anion. So it's going to shift the equilibrium towards making the reactants. You're going to make more acid. If you have excess base or hydroxide coming in, you're going to shift towards making the products. So you're going to make more bicarbonate. That's the buffering system that's set up in our blood. The ratio needs to be 1 to 10 in terms of the acid to the conjugate base. And these are the concentrations that we're looking at with our blood. You can take those and do the math as long as you have the Ka. So this is the Ka for carbonic acid. You can do the same type of calculation that we did in that sample problem, where you rearrange the dissociation expression to solve for the hydronium concentration. And then using the concentrations of carbonic acid and bicarbonate in our blood, we can figure out what the concentration of hydronium is and use that to calculate our pH. So if you use that, it's about 7.4, right? 7.37. So the concentration of carbonic acid is very closely associated with the partial pressure of carbon dioxide. So if you have, you can buy like a monitor for carbon dioxide and carbon monoxide. Carbon dioxide, while it's not really going to kill you per se, but there are negative effects of being in a closed space with high concentrations of carbon dioxide. We're talking about just knocking off IQ points, can make you feel more lethargic and sleepy. So high concentrations of CO2, which mainly comes from being indoors a lot. So, in office buildings and things of that nature where there's a lot of people and not a lot of fresh air being introduced into the environment. So you're kind of breathing in everybody's carbon dioxide. It's not enough to, give you these conditions we're going to talk about, but it is something that you want to consider in terms of just taking care of yourself, being aware of, hey, I've been inside for a while. Maybe I need to open a window, or I need to catch some fresh air. Let me go for a walk, or let me talk with a friend or something. Maybe I'll talk on the phone and just be outside for a quick minute. Keep that in mind. I'm just giving you some life advice here. Anyway, when we're looking at carbon dioxide levels, if you increase those levels, then you're going to increase the amount of carbonic acid. And that means that you're going to make more And I'm putting 2 arrows for, like increase in hydronium, which is the acid, right? And that will lower your pH of your blood. That condition is called acidosis. If, however, you have low amounts of carbon dioxide, then that leads to increase in bicarb. And that will give you alkalosis. So you lower the pH, or excuse me, you increase the pH of your blood, which means that you are becoming more basic. And that's called alkalosis. This table has the symptoms for acidosis and alkalosis, some symptoms, causes, and treatments. So in terms of acidosis, failure to ventilate, suppression of breathing, so holding your breath, disorientation, weakness, and coma. And the causes, there's lots of causes. So it could be something where you have bronchitis or asthma, and that kind of blocks your breathing. All kinds of things, right? You can actually infuse bicarbonate to change the pH of your blood so that it comes back into the normal range. So this is a very interesting table if you're interested in kind of what the symptoms are and the different causes and how you can treat these conditions. Go ahead and read it for yourself. You won't have to know these specific things, like be able to recite this table, but you should understand how acidosis or alkalosis is caused in terms of increasing or decreasing carbon dioxide in the blood. So that's it. Here's your reminders. You've got Mastering Chemistry, Chapters 9 and 11, which those assignments are linked. It's not due until the 22nd. We didn't finish covering Chapter 11 as we were supposed to, but that's fine. So you've got some extra time. And then you have Exam 4, which will be available on November 18th, which is Wednesday. It goes away on Friday, November 20th, so make sure you take it. At least start the exam before 11:59 p.m. You have a final exam. That is Tuesday, December 8th. Normally we do, the multiple days where you can just kind of take it at your leisure. Final exam, that's not the case. 11 a.m. to 1 p.m., that's the window that you have to start your exam, and you get 2 hours. We'll talk about all this in class, so stay safe, and I'll see you then.